All right, so we're going to do kind of just focusing today on perpendicular bisectors. Tomorrow we'll introduce angle bisectors and deal a little bit with what we call construction. And I'll use some constructions today. And when we use GeoGebra, a lot of the things that we do in GeoGebra are constructions, and they're simply creating relationships using circles and straight lines, okay? But also developing, like we'll be able to find the midpoint of any segment using circles and lines, okay? So we'll do a little bit of that. Usually on the intercourse exam, they might ask you a series of steps and say, okay, what did we just construct, or what did we just create, or provide a series of steps that would get you maybe an angle bisect or something like that. So I'll show you how to do that kind of stuff in the next couple days with these shapes. But today, for the most part, talk about perpendicular bisectors. Okay? First thing we got to do is realize what a perpendicular bisector is. And this is a vocabulary word that we've seen multiple times already. We've used it already. But making sure that we're all on the same page and we all understand what a perpendicular bisector is so that we can address the theorem that we deal with in regards to it today. It says a perpendicular bisector is a line or a ray. Okay? And it could even be a segment. So maybe you want to write in your notes maybe that'll be a better definition for us. It's any portion of a line that is perpendicular to a segment at the segment's midpoint. Okay? That is the definition of a perpendicular bisector. Okay? I'm going to use GeoGebra to kind of show you perpendicular bisectors instead of the drawing on the PowerPoint. Okay, if you have points A and B being the endpoints of your segment, okay, and they can be anywhere they want to be. It doesn't matter where A and B show up. Okay, but if I can find the midpoint between A and B, and we have strategies to find our midpoint, don't we? We have the ability to add our x's together, and divide by 2, so it can be 5 over 2. And add your y's together and divide by 2, so it gives me 1 over 2. And it finds me that midpoint, right? Okay. GeoGebra also has the tool to, you click on that second window, go down to midpoint, and just click in the segment that you want the midpoint of. And again, it gives me the same exact spot. Okay. So that point there is our midpoint. I'm actually going to use D, because now it's going to allow that midpoint to stay the same no matter where I move it. It's going to always be the midpoint. When we look at this, any line or portion of a line that passes through D would be considered a bisector. Okay, and we've talked about this in the past. Okay, any line like what I just created, this red line, is a bisector of AB because it takes and it forces those two segments to always be congruent, right? Does that make sense? Because D was the midpoint, so those two segments have to be congruent. But then any line that passes through D is referred to as a bisector of line AB. Is that okay with everybody? Now, we've talked about this in the past. If I look at the angle right there, okay, or its supplement over here, and it doesn't really matter which one I look at. But if I look at that angle, okay, angle BDC, you can start to tell it you know, that line is not perpendicular to AB, right? The red line is not a, it is a bisector, but it's not a perpendicular bisector, right? How many lines, of all these infinite number of lines that are bisectors to AB, how many of them are perpendicular? Just one. Okay, and that's the one right there, right? Beyond that, all these lines are no longer perpendicular. So we have only one perpendicular bisector, okay? But what I need you to understand, because this is something that confuses people sometimes, that red line is doing the bisecting, right? Okay, so the black segment gets cut in half. Does the red line get cut in half? No, that red line, kind of zooming out, kind of maybe presents the idea or concept to you. That red line doesn't have a starting point and an ending point. Lines go on forever both directions. So there's no way to find the middle. Does that make sense? Okay. Now, that doesn't eliminate the possibility every once in a while that maybe we have two segments that are both perpendicular bisectors of one another, but in general, the thing that is doing the bisecting is not always getting bisected. Okay? Any portion of that red segment, or sorry, red line. So maybe I take, you know, that segment there. Okay? That is a perpendicular bisector of AB. That is a perpendicular bisector of AB. That is a perpendicular bisector of AB. Does that make sense, everybody? Any portion of it, if you extend it as rays, perpendicular bisectors of AB. Okay? Now, there are situations, and we'll talk about this a little bit more detail later on, but if I were to take a regular polygon, let's say that has 4 vertices. A regular polygon, the word regular to us just means equilateral and equiangular. Okay, so what I've just created there is a square. Does that make sense? Okay. If I look at the diagonals of a square, the first thing to note is that when I look at J and K, those lengths are the same, aren't they? Okay. When I find this point of intersection of J and K, of these two, we call those diagonals, we get point E, which tells me that distance from A to E, and the distance from E to C, and the distance from B to E, and then E to D. All 4 of those distances are 2.83, right? They're all the same. And another feature of squares is that the diagonals are perpendicular to one another. Does that make sense, everybody? So, what that means is that there are times when you have a perpendicular bisector that is getting bisected. Does that make sense? Okay? So AC is the perpendicular bisector of BD, but BD is reciprocating, is also the perpendicular bisector of AC. Okay? So that does happen. It's not extremely often, but it does happen. Okay? And inside squares is a great place to see that. Okay? Now, the reason we want to talk about perpendicular bisectors and recognize that red line and the features of that red line is because there's certain relationships that exist in regards to points that are on that red line. Okay? If I take any arbitrary point that I want to, as long as it is on that red line, so I'm going to take point E, and I'm going to force it to be stuck to the red line. I can move that point E anywhere I want to, but it's not going to fall off that line. Does that make sense? Okay? Perhaps the most important concept that we talk about in this section for perpendicular lines is the idea that if I'm standing at E, okay, if you're on kind of a bird's eye view here, and you're standing on top of E, and I ask you to walk to A or to walk to B, but walk to the point that is going to provide you the shortest distance, which point would you walk to? Or does it matter? You're standing at E. Which one's closer to you, A or B?
Doesn't matter.
It doesn't matter. Okay? And the reason it doesn't matter is everything that we've already learned in chapter 4. Okay? Think about point E here. Okay? Point E. We've already got A to D being congruent to D to B, right? Okay, D being that midpoint. We've already got this angle here being a 90-degree angle. So what is this angle right here going to be? 90 degrees. Okay, so would you agree that those two angles are congruent? Okay. Would you agree that no matter where I put E, no matter where you put E, that the segment, we're calling it J here, is always going to be congruent to itself? Would you guys agree with that? Okay. No matter where E is, that segment J, or D to E, however you want to call it, is always going to be congruent to itself, even if it comes down here. Okay? Well, think about this. I just asked you to walk from E to A. Well, walking from E to A, when that is phrased, it's the shortest distance from E to A. We want to walk in a straight line, right? We don't want to walk like that to A, right? It's not a very efficient manner. So we're going to straight line from E to A. That distance compared to the distance from E to B, if I look at those two things, what do you notice about them? They're parts of two triangles, aren't they? In this case, they're hypotenuses, okay? But what do you know about the two triangles that they come from? What do you know about that triangle there compared to that triangle on the right? They're what to one another? They're congruent. This side is congruent to that side. This angle is congruent to that angle, right? And this side is congruent to itself. So you got side, angle, side, right? Okay. And no matter where I move E, no matter where E goes, you have side, angle, side. Okay. And we can verify that. We can prove to you that that's 6.35 there, it's 6.35 there. No matter where E goes, now obviously those are going to change, but they always change and end up being the same thing, don't they? Okay? So what that tells us then is no matter where E is, as long as E is on the perpendicular bisector, it will be equidistant or the same distance from the endpoints of the segment that you bisect. Okay? Does that make sense? Now think about this. Some other things that we've already talked about. What type of triangle is ABE? If I find its distances, that's 5.9, 5.9, and E is 7.07. Based on what we've already learned in chapter 4, what type of triangle is that? Isosceles. Okay? And if that's isosceles, haven't we talked about this angle up here? The angle that is not opposite the congruent side, so the angle that is opposite the base, that's called the vertex angle, right? And if we have a segment that goes from the vertex angle perpendicular to the base, doesn't it bisect the base of the isosceles triangle? Okay? And there's also some other features that aren't kind of showing up right here, but these two angles up there, what should you know about those two angles? Angle A to E to D, and angle B, E to D. They should be what to one another? They should be the same, shouldn't they? Should be congruent. Okay? So a lot of stuff that we're talking about today, we've already seen in isosceles triangles. They're the same features. Okay? But what this theorem gets at, this idea gets at, is that, when we dealt with isosceles triangles, we kind of started with a static one triangle idea. Now we start with a point on a perpendicular bisector, and now we learn at that point, no matter where E goes, that point is ultimately going to be the vertex of an isosceles triangle. Okay? But that means then it's going to be the same distance from A as it is from B. Okay? So then we want to know, obviously, the number one question in any math class is, why do I care? Where am I going to use this? That kind of stuff, right? Okay? So let's think that we are some type of entrepreneur, some type of business owner. Don't really care what your company is. But let's say that we want to be able to address two different populations of people, but be fair to them. I don't want to put my company inside, like centrally located inside population 1, where then population 2 has to travel a pretty far distance to get to. Does that kind of make sense? Okay. For instance, think about like the hospitals in Lima, right? They're kind of centrally located in Lima, correct? Okay. We want to put one of those hospitals up in like Columbus Road, right? Because that doesn't benefit the population of Lima. Okay. We wouldn't want to put one of those hospitals maybe on like out in Shawnee on the west side of town, because that doesn't then help the population on the east side, right? Does that kind of make sense, everybody? So think about where you would want to put your business if you had two populations. So I'm going to call these population 1 and population 2. And you want to put your business, so we want to put our business in the best optimal spot for both these populations, right? So they don't have to travel. Population 1 doesn't have a less distance to travel than population 2. Okay. Hopefully you guys realize that the most optimal spot would be the what of that segment right there. If I want the distance from population 1 and population 2 to be the same, obviously I don't put it there, right? I don't put it at the midpoint. If I put it at the midpoint, let's say that's the midpoint there. If I put it at the midpoint, okay, that is then the shortest possible distance that either population would have to travel. Does that make sense? Okay. But let's say that as a business owner, and I'm putting it into an already established community or city or something like that, there's something there already. I can't put my business there. Let's say that there's let's put a lake there. Okay. So if there's a lake there, now we got to figure out if I still want to have the same exact criteria that the distance from population 1 to my business is exactly the same as distance from population 2 to my business is identical. If I want to keep that, I now have to figure out where to put my business. Okay? Well, the theorem that we just talked about says that you put it at a spot on that line right there. You put it on the perpendicular bisector. Okay? And if I can color that real quick. You would want to put your business somewhere on that red line, okay, so that it minimizes the distance between population 1 and population 2 to my business. So I can put it there, or I can put it down here, right? Does that kind of make sense? Those would be the first two places that would make sense, okay? If I put it here, let's find these distances. Let's go attach C to the line. Okay, so those dotted distances, those dotted lines are the distances that my people would have to travel, right? If we look at the lengths of those, H is 5.12, I is 5.12, right? Now, I don't want to put my business there because that is now 6, and 5.12 is a better option, right? That's shorter. So I want to move down as close as I can, and maybe 4.82, right? Does that make sense? Okay. I also have options over here, but my 4.82 is shorter than 4.94, right? So if I could put my business here instead, that would be a better option. And in their case, 4.78 was even better than 4.82. Does that kind of make sense? Okay. That is the reason we investigate and we deal with perpendicular lines. Okay. Any point on a perpendicular bisector is going to be equidistant from the endpoints of that segment. Okay. This all kind of has a foundation in other mathematics. Okay. Have you ever wondered why when you go to McDonald's, what is always across the street from a McDonald's? Go think about any McDonald's that's in Lima. What's across the street?
Burger King.
Burger King. Okay. Go to Speedway. What's across the street? BP or Shell Station or something like that, right?
Yeah.
Okay. Okay. A lot of cities have hospitals, multiple hospitals, right? Lima has multiple hospitals, right? How far apart are they?
Like down the road?
Yeah, like 3/4 of a mile, right? Okay, they're not very far apart. Go to Menards. What's across the street? Lowe's. Okay. Businesses like to cluster themselves, right? Well, the foundation of why they want to cluster themselves is what we're talking about right now. So I want to watch this little video here to kind of explain to you. Now, there's other things that are going on and other concepts that help make these decisions, but this is one of them. Okay. Now I gotta turn my projector on. I don't understand my volume. Sometimes it goes through those speakers up there. Sometimes it goes through my projector. Sometimes it goes through my computer. Before we watch, did you guys ever watch the movie A Beautiful Mind? It's got Russell Crowe in it. Plays a mathematician. He's always like drawing on like windows and stuff with markers, and he sees people. Like he sees imaginary people. It's like schizophrenic or whatever the condition is. You guys watch that movie? It's a really good movie. You've haven't seen it. But it's a true story. Russell Crowe plays a guy named John Nash, who got a mental disease and came up with mathematics that actually won him the Nobel Prize in mathematics. Okay. Actually, it's not the Nobel Prize in mathematics, but I forget what he won the Nobel Prize. Okay. But I don't think mathematics has a Nobel Prize. I think it's a Fields Medal or something like that. However, anyways, famous guy, mental diseases, came up with basically the things that they're going to talk about in this video. Okay, you actually see they talk about a theorem that has his name or a solution that has his name.
Why are gas stations always built right next to other gas stations? Why is it that I can drive for a mile without finding a coffee shop and then stumble across 3 on the same corner? Why do grocery stores, auto repair shops, and restaurants always seem to exist in groups instead of being spread evenly throughout a community? While there are several factors that might go into deciding where to place your business, clusters of similar companies can be explained by a very simple story called Hotelling's model of spatial competition. Imagine that you sell ice cream at the beach. Your beach is 1 mile long and you have no competition. Where would you place your cart in order to sell the most product? In the middle. The 1/2 mile walk may be too far for some people at each end of...
That's kind of what we talked about, right? If I have a business, I want to put it in the middle, right? That's the best spot to put to track both sets of population.
The beach, but your cart serves as many people as possible. One day you show up at work just as your cousin Teddy is arriving at the beach with his own ice cream cart. In fact, he's selling exactly the same type of ice cream as you are. You agree that you will split the beach in half. In order to ensure that customers don't have to walk too far, you set up your cart a 1/4 mile south of the beach center, right in the middle of your territory. Teddy sets up a 1/4 mile north of the center in the middle of Teddy territory. With this agreement, everyone south of you buys ice cream from you. Everyone north of Teddy buys from him, and the 50% of beachgoers in between walk to the closest cart. No one walks more than a quarter of a mile, and both vendors sell to half of.
So there you've kind of midpoints of midpoints, right? You divided the beach in half. Now you get half the beach, he gets half the beach.
The beachgoers. Game theorists consider this a socially optimal solution. It minimizes the maximum number of steps any visitor must take in order to reach an ice cream cart. The next day, when you arrive at work, Teddy has set up his cart in the middle of the beach. You return to your location a quarter mile south of center and get the 25% of customers to the south of you. Teddy still gets all of the customers north in Teddy territory, but now you split the 25% of people in between the two carts. Day 3 of the ice cream wars, you get to the beach early and set up right in the center of Teddy territory, assuming you'll serve the 75% of beachgoers to your south, leaving your cousin to sell to the 25% of customers to the north. When Teddy arrives, he sets up just south of you, stealing all of the southerly customers and leaving you with a small group of people to the north. Not to be outdone, you move 10 paces south of Teddy to regain your customers. When you take a midday break, Teddy shuffles 10 paces south of you and again steals back all the customers to the far end of the beach. Throughout the course of the day, both of you continue to periodically move south towards the bulk of the ice cream buyers until both of you eventually end up at the center of the beach, back to back, each serving 50% of the ice cream hungry beachgoers. At this point, you and your competitive cousin have reached what game theorists call a Nash equilibrium, the point where neither of you can improve your position by deviating from your current strategy. Your original strategy, where you were each a quarter mile from the middle of the beach, didn't last because it wasn't a Nash equilibrium. Either of you could move your cart towards the other to sell more ice cream. With both of you now in the center of the beach, you can't reposition your cart closer to your furthest customers without making your current customers worse off. However, you no longer have a socially optimal solution, since customers at either end of the beach have to walk further than necessary to get a sweet treat. Think about all the fast food chains, clothing boutiques, or mobile phone kiosks at the mall. Customers may be better served by distributing services throughout a community, but this leaves businesses vulnerable to aggressive competition. In the real world, customers come from more than one direction, and businesses are free to compete with marketing strategies by differentiating their product line and with price cuts. But at the heart of their strategy, companies like to keep their competition as close as possible.
So it just gives you an idea of, we're just doing very, I don't want to say elementary, but math that is not as involved as all the math that's taking place in a business owner making decisions on where they put their business, right? What you're seeing as we go through this class and other high school classes, you start to get kind of snapshots and little tidbits of concepts and ideas that get used collectively with other concepts and ideas to help people make decisions in the real world, okay? And that's what mathematics is about. Can we use data, can we use these types of concepts to help us make good decisions, okay? That's why, when I think about this, just kind of an example, Menards and Lowe's, they both kind of constructed themselves at the same time out on the west side of town, right? A couple years later, Home Depot constructed themselves still on the west side of town, but about 1.5 miles, 2 miles further east, right? Okay, like on Cable Road. That Home Depot lasted for like 6 months. Okay, maybe if they would have put themselves closer to where Menards and Lowe's were, that Home Depot might still be in business. Does that kind of make sense? Okay, and people, there are groups in every manufacturer